Your car has a built-in system designed to remove carbon from your engine, and you have probably never used it on purpose. German engineers patented the exact method decades ago. Volkswagen documented it in US patent number 6866031, and the whole process takes about 20 minutes of normal highway driving. But a flaw in modern engine design means this method can actually make the problem worse on most cars sold after 2010. And that flaw is something almost nobody making videos about carbon removal ever mentions. Carbon buildup is not an abstract threat. It's a measurable drag on engine performance, efficiency, and reliability. In controlled dynamometer testing, a 2-liter turbocharged engine produced 324 wheel horsepower when new. After just 10,000 miles of typical city and highway driving, output dropped to 305 wheel horsepower. That's a loss of nearly 10%, enough to turn a quick car sluggish, and it happens quietly, long before warning lights appear. The penalty extends beyond raw power. As carbon accumulates, fuel economy drops and emissions climb. Peer-reviewed studies show that even moderate deposit buildup can increase specific fuel consumption by 3% and raise carbon dioxide emissions by 12%. Drivers may notice rougher idling, slower throttle response, and a persistent sense that something is off. These symptoms are often blamed on sensors or software, but they are rooted in physical residue. Deposits do not limit themselves to a single spot. They form across piston crowns, where they disrupt combustion and trap heat. In the combustion chamber, they insulate surfaces, forcing the engine to burn more fuel to reach target temperatures. Carbon collects in ring grooves, making it harder for piston rings to seal, which increases oil consumption and blow-by. Injectors and exhaust gas recirculation components are vulnerable too, as sticky films alter spray patterns and flow rates, undermining both performance and emissions control. The underlying reason for these system-wide effects lies in the nature of carbon itself. With a thermal conductivity as low as 0.6 to 1.5 watts per meter Kelvin, compared to 15 to 20 for steel, a thin carbon layer acts as a heat shield. This insulation compounds over time, raising local temperatures and accelerating deposit growth. The cycle is self-reinforcing. More carbon means more heat trapped, which means even faster buildup, and a steady decline in how the engine feels, drives, and lasts. A thin film of carbon on metal is more than just a nuisance. It changes the way heat moves inside an engine. With a thermal conductivity of only 0.6 to 1.5 watts per meter Kelvin, carbon is a poor conductor compared to steel, which is around 15 to 20 watts per meter Kelvin. This means even a small layer acts like a blanket, holding heat against the metal beneath. As the engine runs, that trapped heat raises local temperatures, especially around the intake valves and piston crowns. Instead of burning away, new hydrocarbons and oil vapors find those hot spots and stick, forming even more carbon. The process feeds on itself. Each new layer adds insulation, and each degree of trapped heat accelerates the next round of buildup. Over time, the surface temperature in these areas can climb into the 195 to 290 degrees Celsius band, the prime zone for carbon polymerization. Once this cycle begins, it becomes much harder to reverse. High-load operation, especially at low to moderate revolutions per minute, keeps the combustion chamber in the sweet spot for rapid deposit growth. This is where gasoline direct injection, often written GDI, engines are hit hardest. Without the constant fuel wash that older port-injected engines enjoy, GDI intake valves are left exposed to blow-by and oil vapor, baking on carbon that does not easily come off. Testing shows GDI intake valve temperatures often reach 272 degrees Celsius under load, hot enough to grow deposits, but not hot enough to reliably burn them away. The result is a compounding problem. The more carbon you have, the faster it accumulates, and the less effective traditional cleaning becomes. This is the crux of the so-called German method dilemma. Just as drivers turn to high-speed driving to clean their engines, the most vulnerable surfaces in modern engines are the ones least likely to benefit. The so-called Italian tune-up has long been part of car culture, a tradition where drivers are told to run engines hard, revving high and holding full throttle to burn away stubborn carbon. Stories trace the origin to Ferrari mechanics in the 1950s and 1960s. But no workshop manual or first-hand account from that era confirms the legend. Instead, the practice spread as automotive folklore, passed from one generation of enthusiasts to the next, with each retelling adding a new layer of myth. What moves this idea from myth to documented science is Volkswagen's U.S. patent 6,866,031, filed in 2001 and granted in 2005. In this patent, engineers describe a method for removing carbon from intake valves by deliberately operating the engine at sustained high load and speed. The patent details how, under these conditions, the intake valve surface can reach temperatures where carbon deposits begin to break down, not merely blown away, but chemically decomposed in a process known as decarboxylation. Unlike the vague promises of old-school advice, the patent frames this as a repeatable, measurable process, rooted in thermochemistry and surface engineering. This distinction matters. The Italian tune-up is a ritual, and the patent is a technical protocol. Volkswagen's documentation anchors the concept in engineering, showing that under the right conditions, specifically high enough valve temperatures, carbon can be removed predictably. The shift from tradition to patent-backed method marks the point where engine cleaning becomes more than just anecdote and enters the realm of verifiable science. Carbon deposits do not appear at random, they form, break down within a narrow band of temperatures. Laboratory testing and patent documents converge on the same numbers. Deposits begin to polymerize and stick to metal surfaces when temperatures settle from 195 to 290 degrees Celsius. This is the danger zone for carbon growth, where low-temperature oxidation pathways dominate, and each molecule that lands on the surface is more likely to stay. But the chemistry shifts above 325 degrees Celsius. At this threshold, the carbon matrix starts to break apart through decarboxylation. Instead of accumulating, the deposit structure unravels, releasing carbon dioxide and volatile fragments that can be swept into the exhaust. The process is not instantaneous, but it is decisive. The difference between a growing layer and a shrinking one comes down to a few dozen degrees. Volkswagen's U.S. patent 6,866,031 spells out the practical implications. The patent describes a cleaning regime that requires the intake valve surface to exceed 380 degrees Celsius, a point where carbon is not just softened, but chemically decomposed. To reach these conditions, the patent outlines a routine of sustained expressway driving at over 3,000 revolutions per minute for at least 20 minutes. Only then does the valve surface reliably cross the line from deposit formation to deposit removal. This is the technical core behind the so-called German method. It is not about hope or habit. It is about temperature. Unless the metal itself gets hot enough, no amount of high-rev driving will clear away stubborn carbon. Below 325 degrees Celsius, deposits accumulate. Above it, they begin to vanish. The method works when the numbers line up and fails when they do not. Highway driving under sustained load has a reputation in both enthusiast circles and manufacturer guidance for its ability to clear carbon from engines. But the details matter. According to a widely cited but unpublished Audi service protocol, technicians are instructed to hold modern engines at moderate RPM, typically between 2,000 and 4,000 RPM, under real resistance for an extended period. This is not about redlining the engine or revving it in the driveway. What matters is load. The combination of throttle opening and mechanical resistance that forces the engine to generate real heat in the combustion chambers and along the exhaust path. Anecdotes from German TÜV inspectors echo this advice for diesel emissions retests, recommending a long, hard drive on the Autobahn to bring exhaust temperatures up before measuring pollutants. The Volkswagen US patent 6,866,031 formalizes the principle, describing a cleaning routine that relies on sustained high load and speed to push critical surfaces above the temperature threshold where carbon begins to break down, well above what is achieved by simply revving in neutral. Temperature matters, not theatrics. The science is clear. Flooring the accelerator in a high gear at 2,000 to 4,000 RPM generates far more heat in the combustion chamber than spinning the engine to 6,000 RPM without load. That heat is what enables chemical breakdown of deposits. Idle revving, on the other hand, leaves temperatures too low for any real effect. When applied correctly, hard driving can genuinely help clear carbon from piston crowns, combustion chambers, exhaust valves, and piston rings. These are the places where heat and flow work together to remove what normal driving leaves behind. But the method's power has clear limits, and believing it works everywhere is where myth begins to overtake fact. Port fuel injection engines relied on a simple but effective mechanism to keep intake valves clean. Every time the engine ran, gasoline mixed with detergent additives was sprayed by the injector upstream of the intake valve. As the fuel passed over the back of the valve, it acted much like a windshield washer, dissolving and carrying away oil vapor, soot, and the early stages of carbon before they could harden. This constant washing effect meant that even after thousands of miles, the intake valve surface stayed relatively free of stubborn deposits. The detergents blended into pump gasoline were engineered specifically for this job, targeting sticky residues that form when oil and fuel vapors meet hot metal. When gasoline direct injection, GDI, arrived, this protective wash disappeared. Instead of spraying fuel into the intake port, GDI injectors fire directly into the combustion chamber after the intake valve has already closed. That means the back of the valve is now exposed only to air, and whatever oil vapor or blow-by escapes from the crankcase ventilation system. There is no longer a regular flow of liquid fuel to dissolve and remove the accumulating film. Over time, this leaves the surface vulnerable to carbon buildup, especially as the engine cycles through the 195 to 290 degrees Celsius range that encourages deposit formation. The key difference is structural. Port-injected engines had a built-in cleaning cycle every time you drove, while GDI engines lost this advantage by design. Owners may assume spirited driving will have the same cleaning effect, but without the fuel wash, the most critical surfaces are left unprotected. This engineering change redefined the problem, turning a once manageable nuisance into a persistent maintenance challenge for modern engines. Jason Fenske of engineering explained, brought new clarity to the debate with his analysis of SAE research on direct injection engines. The data turned a familiar belief on its head. When engine load increases on a GDI engine, intake valve carbon deposits do not decrease, they build up even faster. This finding challenged the old advice that hard driving would clean the most critical surfaces. Instead, the evidence showed that the very conditions drivers use for an Italian tune-up, wide open throttle and sustained load, are the same ones that accelerate deposit growth on GDI intake valves. Laboratory measurements reveal the mechanism. Under full load, a GDI intake valve reaches about 272 degrees Celsius. That is hotter than most normal driving, but it falls short of the 325 degrees Celsius minimum needed to break down carbon through decarboxylation, the process that actually removes deposits. Volkswagen's U.S. patent 6,866,031 describes this chemical threshold in detail, noting that effective removal requires the valve surface to exceed not just 325, but ideally 380 degrees Celsius. In real-world GDI operation, the intake valve rarely, if ever, crosses that line. Instead, it lingers in the 195 to 290 degrees Celsius window, the prime zone for deposit formation. Every high-load run adds heat, but not enough to tip the chemistry toward cleaning. The result is a slow, steady accumulation, not a purge. The numbers are stark. SAE studies cited by Fenske show that as engine load rises, the mass of carbon on intake valves can increase nearly 9 times compared to low-load operation. The absence of a fuel wash means there is nothing to dissolve or carry away the new deposits. Air alone cannot scrub the sticky layer that forms from oil vapor and unburned hydrocarbons. Even extended high-speed driving, the kind prescribed by the German method, leaves the intake valve below the critical temperature for removal. The traditional logic that more heat equals more cleaning simply does not hold for GDI intake valves. This is the reversal at the heart of the story. The same method that helps older port-injected engines can actually backfire on modern direct injection designs. Instead of burning away carbon, spirited driving may accelerate the very problem owners hope to solve. The gap between 272 and 325 degrees Celsius is not just a technical detail. It is the reason why heat-based cleaning fails on the surface that matters most. For GDI engines, the promise of the Italian tune-up is at best incomplete. The need for engineered solutions becomes unavoidable. Diesel particulate filters, called DPFs, are engineered to solve the carbon problem automatically. No special driving routine or driver input required. Inside the exhaust system, the DPF traps soot and unburned carbon as the engine runs. When exhaust temperatures rise above 350 degrees Celsius during normal highway cruising, passive regeneration begins. At that point, oxygen in the exhaust stream reacts with the trapped soot, turning it into carbon dioxide and ash. If the filter starts to clog before these conditions are met, the engine control unit intervenes. Active regeneration injects extra fuel or adjusts timing to push exhaust temperatures up to 550, sometimes even 700 degrees Celsius. This forced heat cycle burns away stubborn deposits, restoring filter function. Gasoline engines now use a similar system, the gasoline particulate filter, GPF, which relies on the same principle but typically achieves regeneration passively, thanks to higher baseline exhaust temperatures. These self-cleaning cycles are built into the car's software, running quietly in the background. Unlike folklore remedies, these systems are calibrated, repeatable, and proven to manage carbon buildup as part of everyday operation. Dual injection stands as the engineering answer to the intake valve carbon dilemma that direct injection alone could not solve. In 2005, Toyota introduced the D4S system on the Lexus GS 350, combining traditional port injection with direct injection in a single engine. This approach restored a key advantage. Every time the port injector fires, gasoline and its detergents wash over the back of the intake valves, dissolving and carrying away carbon before it can harden. The effect is not theoretical. Field reports and teardown inspections show that D4S-equipped engines maintain cleaner valves even after high mileage, with far less need for chemical or mechanical cleaning. Volkswagen followed with the EA888 Generation 3 engine, launched in the mid-2010s, using port injectors alongside direct injectors to keep intake surfaces clear. Ford's second-generation EcoBoost engines adopted the same principle, blending the power and efficiency of direct injection with the self-cleaning benefit of port fuel delivery. By 2016, Toyota refined the concept further with a self-cleaning injector feature, running targeted cleaning cycles at hot idle to prevent buildup even during extended low-load operation. These systems do what spirited driving cannot. They deliver a controlled, repeatable cleaning action right where it is needed, regardless of driving style. Manufacturers shifted from relying on owner habits to embedding the solution in hardware and software, making intake valve carbon a manageable problem instead of a chronic flaw. Fuel tank additives are often the first suggestion for tackling carbon buildup. But on gasoline direct injection engines, they simply cannot reach the intake valves. The fuel is injected straight into the combustion chamber, bypassing the valve surfaces entirely. No matter how strong the detergent, nothing in the tank will touch the deposits forming upstream. Hydrogen-based HHO cleaning is sometimes advertised as a miracle fix. Yet there is no peer-reviewed evidence in the research presented here to support its effectiveness on GDI intake valves. The best chemical option currently available is CRC GDI IVD Cleaner, which is sprayed directly into the intake tract while the engine is running. It can loosen some of the softer carbon, but even under ideal conditions, it is a partial solution, helpful for prevention and less so for heavy buildup. For stubborn deposits, walnut blasting remains the gold standard. This mechanical method physically strips away 90 to 95% of the carbon, restoring airflow and valve movement. The service typically costs between $300 and $750 for a 4-cylinder engine, depending on shop rates and access. In practical terms, chemical shortcuts and internet gadgets offer little for GDI valves. When real cleaning is needed, direct mechanical removal is still the most reliable answer. Today, Volkswagen's U.S. patent 6866031 and peer-reviewed data prove that heat and load can restore performance, up to 19 horsepower lost in just 10,000 miles when conditions align. But gasoline direct injection intake valves often sit at 272 degrees Celsius, far below the 380 degrees Celsius cleaning threshold, so old remedies can risk compounding new problems. Carbon removal is engineering, not folklore. For modern engines, real solutions require more than a heavy right foot. Share your experience in the comments.